Heat from inside the Earth. So the formation of the Earth, that's where most of the Earth's heat actually came from. And the Earth actually formed similarly to the Sun because basically the Sun and the Earth were originally all a part of the same material. But most of the hydrogen and helium went more towards the center of the solar system, which is where the Sun was created. And then the heavier elements stayed a little bit further out, and they kind of coalesced on themselves. And they kind of they made a formation into a planet. Now in the process, is while they were starting to circle around each other, these particles and this gas and dust, it started to collide into each other, similar to the sun, which increased the heat. And at one point, when all this material collected together, the Earth itself was molten, which means it was hot and it was liquid rock. And the heavier elements in that molten rock, essentially, it all went more towards the center of the Earth. And then the Earth has been cooling off ever since, but it had a lot of heat at which it began with, and it's taken a really long time for it to cool off. Now, just like anything else you can think of, like if you have some really warm cheese, that's a liquid, and then you let it sit there for a while, what's going to happen is the top layer of that cheese is going to be the first thing that gets hard. And that's the same thing that's essentially happened to the Earth. Originally it was all liquid, but then after it cooled off for a while, the top layer became hard, and that's what we call the crust of the Earth. In addition to that, the Earth actually has another process by which heat is actually created from its core. Uranium, thorium, and other radioactive isotopes. Well, we got to pause here. What are radioactive isotopes? Well, if you've taken a chemistry class, you may have seen that sometimes the nucleus of an atom will actually get so big that the nuclear forces that hold the nucleus together aren't strong enough to hold it anymore. So the nucleus will naturally, what's referred to naturally decay or break apart. And in that process, it'll actually release heat. This is referred to as radioactive decay or nuclear fission, and radioactive isotopes actually do this. So basically, we're talking about this process of fission, where particles or where nuclei will break apart, and in the process, they send out heat, and the two particles become a little bit more stable than the entire thing was before. So, in the formation of the Earth, we had these particles that were these elements of like uranium and thorium and other things that have come towards the Earth and kind of went towards the center, and they are naturally going through nuclear fission and creating heat in the process. So uranium, thorium, and other radioactive isotopes naturally decay, which is called fission, and then they produce heat in that process. Now the heat transfers by conduction in the core, but from there, where does it go? Well, before we can really talk about where it goes, we have to talk about what the Earth looks like on the inside. It's pretty obvious that the center is the core, but what's after that? What's above that? So in addition to the core, we have first of all, the inner core and the outer core. The inner core is solid while the outer core is liquid. And the rationale for that is because there are actually two things that cause material, whether it's solids, liquids, or gas, to be in those states. And those two things are temperature and pressure. And they're kind of opposite from each other. So the higher the temperature, material will go from a solid to a liquid to a gas. But when it comes to pressure, the higher the pressure, it'll go from a gas to a liquid to a solid. So if you look at the Earth right here, at the top we have the crust, and in the middle we have the mantle, and then we have the outer core and the inner core. Because the core is so hot, the outer part is a liquid because there's a lot of pressure down there, but there's even more heat, so it remains a liquid. But on the inner core, there's so much pressure that it overcomes the amount of temperature that it has, and then it's a solid because of that. Now, when it comes to the mantle, it's a little bit of a debate on whether it's a solid or a liquid. It's pretty solid, but it still moves. So if you've ever seen a really old church that has some stained glass windows in it, and I'm talking about a church that's hundreds of years old, then you may see the stained glass window is a little bit thicker on the bottom than it is on the top. And what that means is that gravity has actually pulled some of that glass down towards the bottom. Now, you wouldn't call glass a liquid, but it does still, over years, kind of move. Well, that's similar to what actually happens in the mantle. The mantle heats up because of the outer core, and it moves by convection currents, but the amount that it moves every year is really, really slow. And then the top layer of the mantle is actually a part of, well, it's not a part of it. It's a part of the mantle, but it's actually, it moves along with the crust. And those two layers right there, the top part of the mantle and the crust, are actually called the lithosphere, because they move as the mantle produces convection currents, which is something we'll talk about in a little bit. So the outer core is going to be 2,900 kilometers down from the surface. The inner core is 5,100 kilometers from the surface, and the center of the Earth is about 6,400 kilometers from the surface of the Earth. Additionally, the surface of the Earth has two parts to it, two types of crust. You got your oceanic crust, which tends to be a little bit more dense and thinner part of the crust that has conveniently our ocean over it. But then you have the continental crust as well, that's thicker and not as dense as your oceanic crust. So how does the heat transfer? Well, we've already talked about how the inner core and the outer core produce nuclear fission, and they also have the heat left over from the formation of the Earth. So that is transferred by conduction. Then that heat gets transferred into the mantle. Now this is most of the mantle, because the top layer of the mantle is actually a part of is attached to the crust, and those two together, called the lithosphere, those will move together. So most of that mantle, the rest of the mantle left over, has what's called a convection current. It has that heat that's rising upward, and then as it cools, it comes back down and makes this current going around. So the convection from the outer core will heat up and cause the material to go up and come back down. And then you have the process at the crust, where that heat from the mantle is transferred over into the lithosphere by conduction. So the heat is transferred over, and now you have that heat in the lithosphere, and that heat is actually used sometimes. Some people have actually dug holes a couple hundred feet down, and they'll have some sort of like oil through a tube that'll go down, and it'll pick up some of that heat, come up, and through some heat exchange, it'll actually be used to create electricity. So the Earth itself does provide enough heat that we can actually use that in order to create electricity. It's a renewable resource that's possible to use. So the entire process is essentially this. In the inner core, we have conduction by that heat left over from the original formation of the Earth, as well as from nuclear fission. And then the second step is basically most of the mantle takes that heat, and by convection it raises it up to the surface, to the lithosphere, where then it releases some of that heat over by conduction, and then that will heat up the Earth, the surface of the Earth. So then the next question is how do we know all this? How is it possible that we know that the outer core and the inner core, and how far away they are, and the mantle has convection currents and things of that nature? Well, something you may or may not know is that the lithosphere is actually not one solid sheet, not one solid part of the entire Earth. It's actually broken up into pieces, and those pieces are actually referred to as plates. And the thing we know about those plates is those plates get pushed around all the time, and there's evidence that it's getting pushed around by something. So we know that because there are convection currents, that's going to cause the plates to move, and we use this in order to figure out what's actually going on inside of the Earth. So to answer our question, how do we know this? And that's what we're going to get into right now, is we see these plates move. So how does this happen?